Hey everyone, today I'm going to show you guys how to multiply some rational expressions. And we'll start with just monomial terms, just for a simple one, and then we'll move on to some harder stuff after. So for this first one here, we're going to start multiplying it the exact same way you'd multiply a regular fraction. So we have our coefficient here and our coefficient here, so we'll multiply across. 3 times 4 is 12. X to the fourth is the only x in the numerator, so we're going to keep x to the fourth, and our y is the only y in the numerator, so it stays y. And then 2 times 9 is 18. I guess we'll do alphabetical order to keep it consistent. So x squared, then y squared. So next up, what we're going to do is we are going to reduce as much as we can. So our integer coefficients, 12 and 18, are both divisible by 6. So let's reduce top and bottom by 6. And that gives us 2 over 3. Next, we'll look at our x's. Each of our two x's underneath can reduce one of our x's up top. So using your power law, you can think of it as 4 minus 2, or you can just sort of think of each of these sort of essentially canceling one of your x's up top, which leaves us with x squared up top. Now this one here, if you use your power law, you're going to think of it as y to the 1, right? So there's sort of an invisible 1 here. You can think of that as 1 minus 2, which would give you a y to the negative 1 up top. But we don't really want a negative exponent up top. So instead of thinking of it that way, it's actually a little bit faster to think of this 1y up top reducing one of the y's underneath, leaving us with a single y behind. So there we go. We've simplified a rational expression. The problem is that these aren't actually equal, though. And it's not obvious why. The reason why they aren't equal has to do with something called the non-permissible values. Our non-permissible values, usually written as NPV, just because we write it a lot. And these come from our variables in the denominator. So why do variables in the denominator give us non-permissible values? Well, because variables represent any possible number you could substitute. And there are numbers that we aren't allowed to substitute. What's the number you aren't allowed to divide by? You can't divide by 0. So this x being in the denominator means that x cannot equal 0. Because if x was 0, then we'd be dividing by 0. And you can't divide by 0. Dividing by 0 is undefined. Similarly, this y over here means that y cannot equal 0. So in our final expression, we still have a y in the denominator, so we still know just from, the context of this expression that you can't divide by 0, so y can't be 0. But we've lost this part here where x cannot equal 0. That's not in our last expression, but we're supposed to be simplifying this original expression that does have x in the denominator. So every time that you simplify a rational expression, you need to write your non-permissible values. And you can write NP if you like at the end. That's very sloppy V. Let's try that again. NPV at the end. But what you really need to have is this piece right here, which is that x cannot equal 0 and y cannot equal 0. Okay, now we have simplified our rational expression, we've written our restrictions, and our final answer is essentially this entire thing all the way over there. Okay, our simplified expression and our restrictions. Okay, that example wasn't very exciting, right? It's just monomial stuff. Let's try a binomial example so we can see how we can handle binomials. Okay, this next example I'm going to give you guys is already factored. Just so we can focus on the new stuff that we're doing with rational expressions. So let's do 3 of 2x minus 3 over 4 of x plus 5 times, let's do negative 5 x plus 5 x squared over 2 x minus 2 and 3 minus 2x. All right, so we were just talking about non-permissible values. Let's start by looking for our non-permissible values. Our non-permissible values come from anything that's in the denominator. So that, any variable, in the denominator. So here there's an x in the variable, an x variable in the denominator. This binomial has an x in the denominator, and this binomial has an x in the denominator. So each of those 3 binomials is going to give us a different restriction on x. So our first one, x plus 5. I mean, this is a little bit trickier than our last time. We don't just have x on its own. In this case, we're adding 5 to x. So literally, our binomial x plus 5 cannot equal 0. So if we simplify this, the positive 5 on the left, when we bring it over to the other side, becomes a negative 5. And normally we just jump right to this, right? We know we're going to be setting our binomial not equal to 0. And so positive 5 on the left is going to become negative 5 on the right. So let's look at the next binomial, see how that works. We have x minus 2 not equal to 0. So with this negative 2 on the left, imagine this was a negative 2 here, the negative 2 would become a positive 2 on the right. So x can't be negative 5, x can't be positive 2. This one's a little bit trickier. So let's scroll over, give myself some more room. Let's actually write out this whole thing. So 3 minus 2x is not equal to 0. So let's bring the 3 to the other side. So negative 2x cannot equal negative 3. And then when we divide by negative 2, negative over negative becomes positive 3 divided by 2. And so those are your 3 restrictions. X can't be negative 5, x can't be 2, and x can't be 3 over 2. So in our final answer, just like here, we're going to write our restrictions, our non-permissible values at the end. Okay, so that's our restrictions. Now let's go through and see what we can reduce by. I suppose we could multiply out at this point our integer stuff. Our integer stuff we could look at now, though. 3 and 5 have no common factors with 4 and 2. So there's nothing we can do to reduce our fraction in this case. But we can cancel x plus 5 over x plus 5. So x plus 5 divided by x plus 5 is 1, so they reduce to 1. Are there any others? So this one may not be obvious, but there's one right there. And the problem is this negative sign in front is confusing things and making it hard to see what our common factor is. So we always want our terms to be coefficient, positive coefficient with x, and then your constant term, right? You've got your positive x in front, then your constant. Positive x in front, then your constant. This one here, though, has a negative x. And so anytime you've got a negative leading coefficient inside of a factor, you need to factor out the negative sign. Okay, so this next step, we've done a little bit of work. The x plus 5 is canceled. I guess in this step we might as well also do our integer multiplication. So positive 3 times negative 5 is negative 15. And we've got 2x minus 3 is there, and x squared is up there. And 4 times 2 is 8. So we're left with 8 underneath. And our x plus 2 is still there. And this thing here, okay, when we pull this negative sign out, we're going to end up with a negative sign in our denominator. And inside of our binomial, when you pull out a negative sign, essentially what you're doing is you're common factoring a negative 1. So you need to imagine dividing both of these things by negative 1. So negative 2 divided by negative 1 is positive 2. So negative 2x becomes positive 2x. And positive 3 divided by negative 1 becomes negative 3. Well, sure enough, we've got a 2x minus 3 underneath and a 2x minus 3 up top. Maybe you saw that. Maybe you saw that that's 2x minus 3, and this is actually a 2x minus 3. But most students don't. It's really hard to notice that when you've got these leading negative coefficients. So anytime you've got a negative coefficient in front of your highest degree x in your factor, you need to pull it out. And so your 2x minus 3 cancels. Because we common factored out a negative sign, we ended up with an extra negative sign. So it's going to end up being positive up top and positive underneath, because negative over negative is positive. So our final reduced expression is 15 x squared over 8 x plus 2 with our restriction. And our restrictions from our original equation are, let's do ascending order to be fancy. So negative 5, 3 over 2, and 2. So x cannot equal negative 5, 3 over 2, or 2. And there is your complete reduced expression with restrictions.